Hello, and welcome to this Tektronix webinar on 3D stereoscopic monitoring and measurement. My name is Mike Waitson, and I'm an application engineer here within the video product line at Tektronix. You know, 3D is nothing new. Ever since the late 1800s, stereo cards have been used to create a 3D stereoscopic effect. In the 1950s, cinema audiences had the chance to see several films produced in 3D. However, some of the earlier technical challenges meant that it was not really successful. Today, 3D has become more popular, with the advent of digital projection systems and some of the pioneering movies like Avatar that have led the way to increase the popularity of 3D with audiences. Now there is a trend for consumers to have the same experience in their homes, and gradually 3D channels are starting to produce programs for viewers at home. There are several challenges in creating a 3D production, and in this presentation we'll review the technology and the ways to measure the video signals using the Tektronix 8000 series waveform monitors. We'll start by providing a general understanding of the basics of 3D technology and how we create the experience of depth with our eyes and brain. Next, we'll look at how to monitor the 3D signals for the left eye and right eye cameras, and what adjustments need to be made to ensure the correct color balance of the signals. We will then discuss the techniques for monitoring of the stereoscopic 3D signals, and methods for measuring the disparity of the left eye and right eye images. Our eyes are separated by between 60 to 65 millimeters apart. This distance between our eyes is called the interocular distance, and it's this separation apart that gives slightly different views of the images. Here you can see a left and right image, with a slight difference in placement of objects between the left eye and right eye. Our brain interprets these slight differences in order to gauge the depth of objects within the image. When we create 3D stereoscopic images, we are artificially creating this difference between the left and right images, so that our brain will interpret the depth correctly of the objects. Some of this interpretation of depth is based on 2D clues within the image. For instance, an image may have conceals and reveals that indicate whether or not an object is in front of a different object. In the movie theater, images may pop out from the screen directly in front of you. This type of snake effect is somewhat artificial and does not naturally occur. Therefore, we have to create images that have more of a natural 3D look, if we do not want the viewer to get eye strain or make them feel ill. Additionally, when we look at an object in the far distance, we cannot determine a stereo effect. Therefore, there is no stereo effect at infinity or beyond. Our brain can interpret 2D depth clues to determine the relative position of an object. 2D occlusion allows the brain to interpret the depth of the object. For example, in this top image, we have some images that were created in 2D space, yet by placing the object at certain locations gives us conceals and reveals between the objects that we interpret as the sphere being in front. By adding shadows and shading to the sphere, we further enhance the interpretation of depth of the sphere and make it appear to float in front of the image. Textural gradients can further enhance the depth of an object. In the lower images, we've created 3 circles. The first circle, red, is a solid color and appears flat against the screen. The blue circle has been shaded at the top and added a drop shadow that makes it appear to float in front of the screen. For the green circle, we have added a variety of different shading techniques that make it appear that the surface of the sphere is curved and opaque. All these type of effects are used by broadcast 3D graphics systems to create depth in a 2D television broadcast. Perspective within an image allows us to gauge the depth of the objects, and has been used by artists to create depth within their paintings. Here in this photograph, we can gauge the depth of objects within the image by the use of perspective and relative size of objects. We can determine which car is in front of the others. Relative size and position of an object can further determine depth. Take a look at these three horses in the top of the presentation. Most of us know what the relative size of a horse is, so we can use this knowledge to interpret that these horses are at relative distances away from each other, with the largest horse in front and the smallest horse in the distance. Now look at the same objects in the lower part of the presentation. Now the location of these images make it look more like a family, with an older horse at the right-hand side and a little pony at the left. There are a variety of images on the internet that use tilt-shift to give an aerial perspective, which gives an apparent depth to an image. Additionally, motion parallax allows us to gauge the depth of objects as they move across our field of view. Next time you get in your car or take a train, look out the window, and you will notice that you get depth clues by the motion of objects within the image. Retinal disparity we have already briefly discussed. This provides us with the difference between the left and right eye. If you close one eye, then the other as you look straight ahead, you will observe slight differences in your peripheral vision due to the separation of the left and right eye. Our brain stitches these images together to gauge the depth of objects. To create artificially this stereoscopic view, we need two cameras that can be placed side by side within the rig. The distance between the two lenses is known as the interaxial distance. This distance can be varied by the camera rig, and does not have to be 60 to 65 millimeters to replicate the human vision system. Creating this artificial depth will depend on the distance of objects within the scene, from the camera and the distance apart of the two cameras. You know there's an app for that can be used to calculate the stereoscopic depth of your scene. Both cameras need to be matched in terms of video levels, so that they are identical. Similar, the focus and zoom controls of the two cameras need to be synchronous and matched, and the two lenses should also be matched. Careful positioning of the camera on the tripod and controlled movement of the rig should be done, otherwise this can cause distortions to the 3D effect. The other alternative for creating stereoscopic 3D is with a beam splitter mirror rig. These rigs are more complicated than the side-by-side rig, but give greater control of the 3D effect. The cameras can be mounted in a variety of ways, where one camera views the image directly, passing through the mirror, and the other camera is placed above or below to view the reflected image from the mirror, as shown in the diagram. The mirror rig allows the two cameras to see the same field of view, and allows a variety of mechanical controls to adjust the position of the two cameras. Due to the mirror, one of the images is inverted, and electronic processing is required to flip the image. This can cause delay in the video processing of the images, which needs to be accounted for in the system. Whether you are using a side-by-side or mirror rig, you can choose to have the two cameras either parallel or converged. There are certain advantages and disadvantages with each method. A parallel rig is simpler to operate. However, you can have a wide variation of disparity within the image. The convergence of the final 3D image can be decided in post-production later. In a converged application, the rig is more complex, and the convergence of the image has to be defined on set. That fixes the disparity of the image that can give more control to the amount of depth present. However, it is not possible to unfuse the background later in post-production. The interaxial distance is defined as I between the two cameras, with the distance from the camera to the object defined as D. Now the angles that the object subtends between the two cameras is shown in the diagram and produces the following equation. If we now look at the images from the two cameras, we can observe the horizontal disparity difference between the left and right eye. Our brain will then use these differences to calculate the depth within the image and determine which objects are in front or behind. In this case, we assume that the cameras are aligned vertically, as vertical disparity is not a naturally occurring phenomenon. Now let's take a look at some of the terms used to define the depth of an object. Parallax defines the difference in position of an object between the left eye and right eye views. Here we have two images, a left eye view and a right eye view, which, if superimposed over each other, show the difference of the objects within the image, as shown in the lower pictures. We can therefore define the relationship of an object in terms of the object's retinal disparity, and this is described by four different types of parallax. Zero parallax is when there is no difference between the left and right eye, and the object is at the screen plane. Positive parallax is when the object appears to be behind the screen. Negative parallax describes the objects that appear in front of the screen. Divergent parallax is not natural, but can be created in stereoscopic 3D, and should be avoided. Let's take a look at these different kinds of parallax in more detail. Zero parallax is when the left and right eye views of an object are exactly superimposed. In this case, the object will be perceived at the surface of the screen. This is an important reference point in stereoscopic 3D, and is called the zero parallax plane. Notice that our eyes will be slightly converged onto the objects at the screen plane. For positive parallax, the object is perceived to be behind the screen plane. This is because the right eye location of an object is to the right of the left eye location. In this case, the views of the object are more diverged and become more parallel in nature. The eye muscles are more relaxed, and viewing of the objects will be more comfortable. Negative parallax is when the objects appear to pop out in front of the screen. This is because the right eye now sees a shift to the left of the location seen by the left eye. The brain interprets the object as appearing at the intersection of the left and right eye view in front of the surface of the screen, and appears to float in space. The eyes will become more and more converged the greater the depth of the object. This can result in more strain on the eye muscles, and introduce more fatigue and illness if the viewer has to view these objects for prolonged periods of time. Divergent parallax is a biological limitation to the amount of positive parallax an image can have. The eyes should never be required to diverge beyond parallel. Therefore, the left and right location of an object must never be displayed more than the distance between the eyes of the viewer. If divergent parallax occurs, it will put a strain on the eyes and brain as it tries to fuse the images together, and may cause a person to feel ill. For 3D stereoscopic imaging, we have to develop viewer tolerance limits, so that the viewer does not experience discomfort of total divergence or excessive convergence that will cause strain on the eyes and brain. From the screen plane, we have zones of parallax that will be acceptable for the viewer. Note the amount of disparity difference will depend on the screen size and the distance the viewer is from the screen. Therefore, in the movie theater, if you sit closer to the screen, the depth experience will be different than someone who sits further back in the theater. Similarly, the amount of disparity allowed on a larger cinema screen will be different than that of a viewer at home watching on a smaller TV. At Tektronix, we have created a 3D test pattern using the TG700 signal generator platform. This 3D test pattern requires two HDVG7 modules or a single SDI7 module in order to generate the separate left eye and right eye test signals. The frame patterns are then loaded to the TG700 mainframe and assigned to the appropriate generator outputs, one for the left eye and the other for the right eye. Here we can see the left eye and right eye test patterns. You will notice that the outer edges are identical for the left and right eyes, and the convergence pattern crosshairs are present to ensure alignment of the left and right images. In the center of the two images are a series of objects with horizontal displacement. Notice the pole in the center of the image, and the difference between the position of the object in the left and right eye views. In this case, the pole appears to come out of the screen. Text at the bottom of the screen confirms that the right eye and left eye are correctly displayed when one or other of the viewer's eyes are closed. So far, we have explained the basic concepts of stereoscopic 3D. Now let us turn our attention to how we can monitor the 3D signals. On the WFM 8300, or with the 3D option installed on the WFM 8200, you can monitor a 3D signal either as a dual stream left eye and right eye signal in either two separate HD-SDI signals, or a level B 3G signal that is a multiplex of the two HD-SDI signals. Simply press the front panel main button and select the 3D type to be dual stream 3D. Using the SIM mode of the waveform monitor, it's possible to configure a left channel and right channel presentation separately. Select the main button and enable the simultaneous mode. Now you can configure channel 1, tiles 1 and 3, for the left eye, and channel 2, tiles 2 and 4, for the right eye of the display. You can choose any of the 3D display modes for any of the tiles. Tektronix developed SyncView to simplify 3D monitoring configurations. To enable SyncView, select the function from the main menu. Once configured, whenever a change is made for one channel, that display is automatically mapped to the other channel. For instance, if gamut is selected for tile 1, then the display will automatically be configured for tile 2, thus simplifying the configuration of 3D measurements. Note, SyncView does not affect the 3D modes in either trace or picture display. That means left and right channels can be maintained, or different 3D picture displays can be used in sim mode. You can also select a side-by-side, top-bottom, or field interlace 3D mode, where the left eye and right eye signals are split into two separate parts of the HD-SDI signal. This mode is accessed from the main button, and the user should select the appropriate mode for the 3D type within the instrument menu. There are a variety of 3D picture display presentations that can be configured within the instrument. An overlay of left and right images superimposes the two images on top of each other. Alternatively, the user can select only the right or left eye view. This is useful in sim mode when channel 1 views the left image and channel 2 views the right image. A difference map shows the degree of difference between the left and right image. A 50% gray image would mean that the left and right images were identical. The anaglyph presentation can be viewed with red cyan or green magenta glasses. This is a monochrome anaglyph, so it's easier to see the depth without seeing false colors. A checkerboard display shows a block of the left image followed by a block of the right image, forming a 16:9 checkerboard pattern that allows the user to discern luma and color differences between the signals. We are artificially creating this stereoscopic 3D effect, and it's important for the video image to be as natural as possible to what we would typically see. If we change what our eye and brain expects to see, this can cause fatigue on our eyes and cause our brain to misinterpret the image, and this can result in making people feel ill. Within the camera rig, it is possible to change the vertical position of the two cameras. Our eyes cannot be vertically offset, and therefore a large vertical offset between the left and right images will cause people to have to strain their eyes to view them. This strain could cause discomfort and make a person feel ill. When horizontal parallax is out of control, this will produce a large difference in the object between the left and right eye. This will cause the eyes to have to excessively converge or diverge the image. This will put additional strain on the eye and brain in trying to fuse the two images together. In some cases, a person may no longer be able to fuse the two images together and see two separate objects. Therefore, the degree of horizontal parallax should be limited to a suitable range. Note that people can tolerate more depth behind the screen than in front of the screen. Therefore, excessive negative parallax should be limited. Changes in brightness or color between the left and right images can cause disturbance to the viewer. In tests, when the image to one eye was made darker than the other, people would eventually take off their glasses and rub their eye, since they believed something was obscuring their vision. Therefore, it's important to ensure that the left and right cameras are correctly balanced and aligned. The filters used to separate the left and right eye are not perfect, and this may cause the right eye to see part of the left eye image, and the left eye to see part of the right eye image. That gives rise to a ghost effect. There are various methods devised to reduce or eliminate this ghosting effect for the viewer. However, residual information can cause confusion and strain for the viewer. As I mentioned earlier, the screen plane is an important reference point in stereoscopic 3D. During production, certain scenes may have been produced that change the location of the screen plane. This will cause confusion and disturbance for the viewer, as this is not a natural phenomenon. Ideally, the screen plane for all shots should have been defined at the start of production. If this is a critical scene within the production that has the error, then in post-production the editor should bring the image to 2D before changing to the next scene. This could be done by fading to black between scenes or making the images only be 2D for the transition. As I mentioned earlier, the screen plane is an important reference point in stereoscopic 3D. During production, certain scenes may have been produced that change the location of the screen plane. This will cause confusion and disturbance for the viewer, as this is not a natural phenomenon. Ideally, the screen plane for all shots should have been defined at the start of production. If this is a critical scene within the production that has the error, then in post-production the editor should bring the image to 2D before changing to the next scene. This could be done by fading to black between scenes or making the images only be 2D for the transition. Objects at the edge of a scene may only be present in one eye, and again this can cause confusion and disturbance to the brain, as you can see in the two illustrations. To correct this type of issue in post-production, a vignette of the image can be performed, such that the edges of the image are much darker and more difficult to distinguish. The other alternative is to make the object at the edge have zero disparity and be identical in the left and right eye. Therefore, the other objects in the scene will have a positive disparity and appear behind the screen plane. Tektronix has developed a set of tools to assist in stereoscopic 3D monitoring and measurement, and in this next section we'll discuss how to use these tools. During production, the left and right images may have differences in luma or color difference channels that indicate that the two cameras are not identically adjusted. As you can see from these two images, the left eye is much brighter than the right eye. You can use the checkerboard picture display to help easily identify the differences between the luma levels or color difference channels of the two images. The checkerboard display is comprised of blocks of the left then the right image in a 16:9 checkerboard pattern. The waveform or diamond displays can then be used to correct for the differences. Here we have configured the sim mode of the waveform monitor to show the RGB diamond trace displays along with the left and right picture displays. SyncView was used to simplify the configuration of the displays within the instrument by automatically configuring the left and right channels with the same set of displays. In this image, a lens flare was produced due to the slightly different locations of the two cameras. In the left eye camera, branches obscured the sun, while in the case of the right eye camera, the sun peeped through the trees and hence produced a distinctive difference between the left and right eye views. In this case, the picture difference map can easily show the difference between the two images. Note when the object is only present within one signal, the picture difference will either be full white or black, depending on whether the difference map is left minus right or right minus left. Alternatively, the anaglyph display could also be used to help the user visualize the 3D effect between the images. Differences in focus or softness between the left and right image can cause problems for viewing 3D stereoscopic images, causing problems for the brain to fuse the objects within the scene. Here you can see the left eye image is more blurred than the right image, which is in focus. The difference map in this case can show the left minus right image, and can be used to check the placement of the objects within the scene. If the image was at a 50% grey, then there would be no difference between the left and right eyes. Typically, for moderate disparity between the left and right eyes, the image will have an embossed nature to the display. The larger the difference between the left and right images, objects will produce white or black regions within the display, depending on whether the difference is due to the left or right eye. An incorrect zoom on the camera can shift the perspective between the left and right eye views, and cause problems for the brain to be able to fuse the objects together. If we look at the zoom difference between the left and right eye views within the left minus right difference display, you can see the large black and white differences in the image, and the vertical shift between the left and right images. The user can then adjust the zoom position of the camera to remove this difference between the left and right eyes. The anaglyph display modes allow the user to visualize the depth within the image when the user wears the appropriate colored red cyan or green magenta glasses. Note that when wearing these type of glasses, the display is a monochrome anaglyph, so it is easier to see the depth within the black and white image, and will not produce the false colors that are typical when viewing other types of anaglyph presentations. Therefore, if parts of the image are gray, then they are identical between the left and right eyes, when viewed without glasses. The color difference of an object identifies a depth difference. For measurement purposes, a disparity grid can be overlaid on top of any of the 3D picture displays to allow the user to gauge the disparity difference of an object within the image. The grid can be configured for a width of 1% to 15% horizontal disparity, and a vertical grid line can be added for 50, 25, or 10%. This disparity grid is very useful when you are setting up the cameras in the studio or on location to identify the depth of objects within the scene. For precise measurement, a disparity cursor can be positioned within the picture display to find the disparity of an object. The measurement can be made in terms of pixel difference or percentage of the screen width. For instance, in a 1920 by 1080 image, a 1% horizontal disparity is equivalent to 19.2 pixels. An A-B waveform mode can be used to show the difference between the left eye and right eye waveforms. For instance, this can be used to determine the black level difference between the left eye and right eye cameras. However, Tektronix has developed the quad diamond display that can aid users adjust video levels between the left and right eye cameras more easily. We have already mentioned how the checkerboard can aid in determining luma and chroma differences between the left and right cameras. Once an error has been determined within the images, the Tektronix quad diamond display can be used to make adjustments of the signals. When in the 3D mode on the WFM8300, press the gamma button, and then push and hold the gamma button to access the menu. From this menu, select the Tektronix patented quad diamond display. I have selected the pseudo color mode for the traces within the display to help visualize the information more easily. In the next few slides, we'll explain how this display works. The Tektronix quad diamond display has 4 gradicules for each of the color components: luma, red, green, and blue, as shown within the display by the colored gradicules. However, unlike the typical diamond display, which is a G versus B or G versus R, as an XY plot of the signal, the quad diamond display is a disparity histogram of the left and right channels. Like the diamond display, black is at the lower apex of the diamond, and white at the upper level of the apex. If the left eye and right eye signals were identical, the trace would form a vertical line, since this would mean there would be no difference between the left and right eyes. When there are differences between the left eye and right eye, this would cause a deviation of the signal in the horizontal direction. The horizontal axis therefore shows the disparity between the left and right channels, and the amount of spread gives a gauge of the total disparity between the signals. This can help in aligning the cameras for the stereoscopic scene. For a correctly aligned left and right image, the trace would form a vertical blob within each of the diamonds. If the trace is not vertical, as with the blue trace in this display, this would indicate an imbalance in the blue channel between the left and right eye signals, and would require the user to make adjustments of the signals to correct for this error. Creating the illusion of stereoscopic 3D needs careful consideration in the production process. The images need to appear natural and typical of what the eye and brain are used to. If errors occur within the left and right images, the eyes may become strained, and this will cause fatigue or make the person feel ill. Therefore, careful attention needs to be taken in 3D production, and Tektronix offers a variety of measurement tools to aid in monitoring of stereoscopic 3D. The patented Tektronix quad diamond display can be used to ensure alignment of the two cameras and that they are correctly balanced. Thank you for attending this webinar on 3D monitoring and measurement. You can find a wealth of other information here on the Tektronix website, from application notes such as a guide to standard definition and high definition measurements, and to product information on the WFM